In this video I will give you all the essentials you need to properly understand the Coulomb force between charge carriers such as electrons or protons. And also I will show you the concepts of electron gas and of drift velocity, which will enable you to fully understand where the famous Ohm's law comes from and how it can be derived directly from the Coulomb force. My name is Andreas from The Fearless Engineer. Let's go! In the last video on atoms and charges, we have already seen that electrons and protons, they exert a force on each other, which is either attracting or repelling depending on the sign of the charge. And this force is called electrostatic force or Coulomb force, and it's the basic mechanisms by which we can move electrons through a conductor. Why is this important for you? Because it allows us to transport energy and drive all of our electronic devices, ranging from a smartphone up to an electric vehicle. And to understand how this works, we need to discuss three major topics. The first is what is the electron gas? The second is what's the Coulomb force and what's the electric field? And the third is what is the drift velocity of electrons? While this video is mainly about the theory behind the Coulomb force, the next two tutorial videos will look into what you can actually do with the things you learn in this video here. And in case you're interested, you can download all the slides, the learning materials, also circuit diagrams, which you see in my videos directly on my website at thefearlessengineer.com. Link is down below in the description. And this video is actually part of a basic course in electronics, and if you feel like watching the other parts of it as well, you can find the corresponding playlist in the description and on my channel, also on my website. And if you feel like it, then please consider subscribing to my channel. And if you do so, don't forget to ring the bell, because like this you immediately know when the next video goes online. Oh, and by the way, if you have any questions or you do not understand something fully, then just click pause and write me a comment down below in the comment section. I'm happy to help you. So now let's start with the introduction to the Coulomb force, the cause for the movement of charge carriers. In this module on Coulomb's law, we want to dive into the reason why things work in electronics. We want to understand how light bulbs can shine, how electric cars can drive, and how you can actually watch this video on your smartphone monitor. In order to understand this, you need a little bit of theory. And this is what this video is about. It's part one, the theory section. And in this theoretical part, we want to discuss three major concepts. The first is the concept of electron gas. Then we discuss Coulomb's law, the Coulomb force between point charges, and then thirdly we want to dive into the concept of drift velocity. This is the velocity, the speed of electrons as they move along through a copper wire, or through any wire by that means. And in part two, which are the upcoming videos, two in this case, we want to first compute the Coulomb force between two point charges in space. We want to know how strong they repel or attract each other depending on the sign of the charge. And then secondly, in the second tutorial video, we want to compute the amount of charge which passes through a wire in a given time unit. We have already seen that particles, they exert a force on each other based on the amount of charge which they bear. For example, we have discussed electrons and protons. We also have discussed the concept of the elementary charge, and you can of course compute the amount of force between two elementary charges, but you can also group several elementary charges together, let's say 20 or 20,000 or 20 trillion, and then observe how strong the force is which they exert on each other. And this phenomenon of charges exerting force on each other is called electrostatic force, or also Coulomb force. And thanks to this electrostatic force, electrons will push away other electrons and they will be attracted to positive charges such as protons. And this force is basically the glue that holds atoms together, but it's also the tool we need in order to conduct, to move, to push, to pull electrons through a circuit. Now, why should we be concerned with moving electrons along? Well, because we can move them to transport energy to certain points in an electric circuit, to power a light bulb, and to drive the monitor you're currently looking at. This is the reason why we need to discuss the Coulomb force. It drives everything we use in electronics. Now, in order to explain the principle of moving electrons through a conductive material such as a copper wire, we need to make use of a model. Models are used in abundance everywhere in physics, in mathematics, in chemistry, and they help us understand and describe what's happening in the world by means of equations and parameters. Now, if you look into the literature, you will find several models to describe the motion of electrons through a medium. One of the most well-known models is the band model, which we will look again in the future when we discuss semiconductor physics. And also we have the model of electron gas, which we'll use here in this model, because it helps us to explain the flow of electrons through the space between atoms very intuitively, and from this we can grasp the reason how we can propel electrons by means of an electric field, which is related to voltage and it leads to a current, and it very neatly converges into Ohm's law at the end, which you'll soon see. And in order to understand this model, let's consider a copper atom, which you can find in the lower left corner here. Now the force with which electrons are attracted to the nucleus, it decreases with growing distance. This is something we have already talked about in the video on atoms and charges. And electrons in the outermost orbit, which is the one with a red circle around it, they are only very weakly, they are weakest attracted to the center core, and they are called valence electrons. Now, while copper has only a single valence electron in the outermost orbit, if you take another material, for example aluminum, there you will find 3 valence electrons. And this is of importance later when we compute, in the first tutorial, when we compute the number of freely moving charges in a medium. Now, when several copper atoms combine to something larger, for example a piece of copper wire or a copper coin, which we already took a good look at in the last tutorial video, they form a so-called lattice structure. And the lattice structure is basically a highly symmetrical grid, and when they do this, when they arrange themselves into this energy conserving form, they give off some of their outer valence electron. Each atom gives away a single valence electron, and this means that in the space between the atoms which are locked in this highly symmetrical grid, in this lattice structure, we have a number of particles, a number of electrons which are allowed to move around freely. And this cloud of electrons which floats around in the space between the atoms, this basically looks and behaves like a floating cloud of gas particles, hence the name electron gas. Of course, it's not an actual gas, but the number of electrons which move around in this gas-like fashion, it resembles a gas in chemistry. Now that we understand what the concept of electron gas is, we want to find a way to move it along in a certain direction in our wire in order to have it transport energy into our circuit. And this is where we come to the Coulomb force. Now that we have a model for describing charge carriers, which are the electrons, within a conducting medium, for example a copper wire, what we need is a source to induce this movement. And before we get to such a source, we must first describe the electrostatic force that acts in between charged particles. And as far back as the 18th century, Charles-Auguste Coulomb, a French scientist, he carried out some systematic research into the effects of charged bodies on each other. And what he managed to do back then, with a very sophisticated apparatus he built, he was able to describe the force between charged bodies, 2 or 10 or 20, depending on 2 major parameters. The first is the amount of charge which a body carries, and this is abbreviated by the symbol Q, small q in this case, and also on the distance r between them. So if you only take 2 bodies, as you can see in the small diagram here, you have a positively charged body which is indicated by Q+, and then you have a negatively charged body which is the blue circle, Q-. The force F in between them is basically dependent on the amount of charge in Q+ and Q-, and on the radius r, or the distance r, between the 2 bodies. Now, if we consider a point charge, Coulomb's law assumes that the potential of this charge to exert force on another charge somewhere is equally distributed over an enclosing sphere. That means we have a center charge, we imagine ourselves a sphere around it, and we make the radius of the sphere extend to the position of, let's say, the second charge, or the third charge, or any charge anywhere in space. And of course, the surface area of a sphere with a radius r is equal to 4 pi r squared. This is basic math which we use here. And now we take the amount of charge q, which, as we stated before, can only be an integral multiple of the elementary charge. Let's say 10 elementary charges. Let's imagine 10 electrons as the point charge, and the electric field is nothing more than a charge divided by the surface area of an enclosing sphere in a certain distance r. And also we have a constant epsilon 0 here, which is called the electric constant. It's 8.854 times 10 to the power of -12 Coulomb per voltmeter. We will talk about the units later on, and it describes the permittivity of vacuum for an electric field that permeates this vacuum. So the electric field, a very important concept in electronics and electrical engineering, is nothing more than charge divided by surface area times the permittivity of the enclosing matter. Now let's place 2 charges in space. We have a charge Q1 and a charge Q2, and we want to know how large the force in between those 2 point charges is. In order to do this, we can simply take the field which is generated by the first charge, E1, at the position of the second charge, and the distance in between the 2 charges is R12, and then we simply multiply this electric field at this position with the amount of charge of Q2. And we can also do this vice versa. We can look at the electric field generated by the second charge, E2, at the position of the first charge, multiply it with Q1, which is the second line of the equation you can see down below here. And what we get is the product of both charge amounts, Q1 times Q2, simply divided by the enclosing sphere, which is given by 4 pi times r squared, and then multiplied by the permittivity of the vacuum. This is the force of the first charge on the second charge, which is identical to the force of the second charge on the first charge. And note that in this tutorial here, we are ignoring the directional component of F. You can compute this, of course, for much more complex constellations of charges anywhere in space. You can also look at the direction of the forces, but this is nothing what we want to do here. We only want to look at the base concept, which is in its most simple form, the force between 2-point charges, without looking at any directional components. And if you look at this diagram here, what you can see on the left side is a cloud of positively charged particles, and on the other side you can see a cloud of negatively charged particles. And if you place these multiple particles in a certain distance of each other, somewhere in space, what you get is an approximately homogeneous electrical field in between these two clouds. And if you place a small, let's say in this case negative charge, somewhere in the middle of the field, in between these two stationary particle clouds, you will observe that this small particle will drift to the left towards the positively charged cloud because it's pulled by the charges with the opposite sign, and it's also pushed by the charges with the same sign. So it actually has two forces which work on this particle. We have the force depicted in red and we have the force depicted in blue, and both forces propel this body from one side to the next. And this is the basic principle of a battery in electric circuits. We have a particle, let's say a charged electron somewhere in a wire. We have a battery attached to the wire, and this battery generates an electric field, and this field is responsible for the particles moving through the wire. Even though electric fields inside conductive materials such as metal is an entire topic for itself, and actually you will find that there is no electric field inside, but the reason for the electrons moving through the wire is induced by this concept. And in the image you can see here, we assume that both particle clouds, the positively charged side and the negatively charged side, they hang somewhere in space, and we have a free floating electron in between the two. Now, if we subject a lattice of copper atoms, for example in our copper cable, to an electric field, for example induced by a battery which we connect to the wire, we will see that the free electrons inside the wire, they will start to drift against the field. You can actually see this in the small video here. We have the large blue copper atoms here. We have the valence electrons which have been freed by the atoms bonding with each other, and the electric field is depicted by a green vector arrow. And once you apply this field, you can see the movement of the red particles of the electrons through the space in between the atoms in a homogeneous direction. And the flow of electrons in a conducting medium, for example copper or aluminum, under the influence of Coulomb force is what we actually call electric current. Now let's take a look at the velocity with which electrons move along in a wire in a conductive medium under the influence of an outside electric field. And this field actually causes the electrons to drift along, which is why the speed at which they do this is called drift velocity. And in its most basic form, the drift velocity is simply given by a product of two terms. The first is called the electron mobility, and the second is the well-known electric field E. Now for copper, the electron mobility is at 44.2 centimeters per voltage second. Let's ignore voltage for a few more minutes until we get to the next video, but for now we just look at this value and we can see that obviously the drift velocity is material dependent. This means if we replace our copper wire with a piece of aluminum wire, the drift velocity is going to be different if we leave the electric field, which is the other parameter in the equation above, the same. Now let's make a small example here. Let's assume we have an electric field of 0.1 volts per centimeter and we have the electron mobility as given above in copper. Then the drift velocity results to only 4.42 centimeters per second, which is, if you think about it, actually really slow. Maybe you had the notion that electrons would move along at light speed, which is, as you can see here, completely not the case. And this poses the interesting question why flicking the switch on the wall causes the light bulb on the ceiling to switch on immediately. We have just seen that the electron which is sitting behind the switch takes a few minutes to get up to the ceiling, but the light shines immediately. And the reason why this happens is that the electron sitting directly in front of the light bulb also starts to move once you flick the switch. So the electric field which induces the motion into the electrons works on all electrons at the same time, or almost the same time, and this is why the light switches on immediately. And now we have covered all the basics to understand the flow of current through a wire. Let's sum it up. Now the model of electron gas, which we have taken a very close look at here, explains how free electrons and thus charges behave and move in a wire, for example a copper wire. And the electric field describes the ability of a charged body, or point charge or any other charge, to exert force on other charges which are located somewhere in space. And the product of an electric field, which is caused by a first charge multiplied with the amount of a second charge, gives us the electrostatic force, the Coulomb force, between these two charges as a function of charge amount and relative distance between the two charges. And when we connect a battery to a wire, the electric field, which is induced by the battery poles, causes the electrons, the free electrons sitting in the wire in between the atoms, as we saw, to drift towards the positive pole. So the negative pole pushes away the electrons while the positive pole pulls them towards it. And here's the outlook on the upcoming 2 tutorial videos. We want to see how we can calculate the Coulomb force between 2 point charges. We're actually going to compute this, and we're also going to relate it to the forces in a Tesla Model 3. And in the second tutorial video, we want to calculate the amount of charge which passes through a conductor in a given time instant. In this video, I was mainly focused on the question of how to make electrons move through a conductor in a more or less orderly fashion. And once we have understood how this works, we can almost explain the terms current, voltage and resistance, which are the basic measures which we have in electronics. But before we do that, the next 2 videos, which are tutorial videos, will be about what we can use the knowledge from this video for. This could be, for example, to compute the force between 2 point charges in space and compare the results with the forces at work in a Tesla Model 3 electric vehicle, or we can, for example, derive how many charges per time unit actually move through a piece of wire. And if you're interested in how this works, just take a look at the next video in my electronics playlist. The link is of course down below in the description and above in the cards. And if you like this video, please consider subscribing to my channel, and if you do so, don't forget to also ring the bell, because then you'll know immediately when the next video goes online. And also you can find all the slides and circuit diagrams and learning materials which you see in my videos for you to download for free on my website at thefearlessengineer.com. So have fun, see you next time here on The Fearless Engineer.